Hello, good day, doctor. My name is Kelvin Chai. The matrix number is AE180101. So we start our presentation now. We are from Group 5. The group member have Cheng Wei Lun, Wong Chun Xiang, Yap Ken Hua, and Liu Keng Chun. Next is introduction. So in this project, we are required to build a separate set of AM transmitter and receiver system that can transmit the signal. So based on MCMC allocated frequency, the frequency range is between 550 kHz to 1720 kHz. So this project, we are choosing the transmission frequency is 1000 kHz. So the purpose for our project is the AM transmitter transmit the audio signal with a carrier signal by changing the amplitude of the input signal, and the AM receiver is used to demodulating the AM signal to its original signal within a certain bandwidth.
Good day to doctor. My name is Yap Ken Hua, matrix number AE180096. So today I'm going to present the whole design of the transmitter of our AM modulator. So I'm start the whole design step by step. So this is the whole design of our transmitter of the AM modulator, and the whole design is a high level AM modulator. And from the beginning we can see this is input. So this is the input of the input signal, so which is the modulating signal, and this part is a pre-amplifier, and we can see there's a little resistor here. This is the emitter resistor of this amplifier, and this is a decoupling capacitor. So it decoupling the emitter resistor and realizing the full gain of this stage. Okay, so this is the function of this capacitor, and we can see there's another input here. So this input is carrier signal. So the carrier signal is sent into the base of this transistor, and this transistor is a radio frequency oscillator. So this is the amplifier before the modulator signal sent out. Okay, so this is a emitter resistor. So this resistor ensure the oscillation will not shunt to the ground. So this is the ground of the circuit. So beside the emitter resistor, there's a decoupler capacitor here. So the decoupler capacitor here is used to decouple the resistor, the emitter resistor, and ensure the gain requirement is fulfilled. So basically the whole oscillator is used for the modulator to vary the voltage and power for the whole modulator. So this make the modulation high efficiency and make a high quality performance. So above this oscillator, this is a little tank circuit. This is a LC circuit. So this tank circuit basically it control the frequency of the oscillation. So we need to set the value for this tank circuit to control the frequency of oscillation, so that the modulator can be done smoothly. And between the tank circuit and the oscillator, the amplifier, the output is get from here and sent to the receiver, which is the demodulator, and demodulate and recreate the signal again. So this is my part. Thank you.
Hi, a very good day to a doctor. My name is Liu Keng Chun. My metric number is AE1800S7. Today, I will present about the whole design of receiver on our AM modulator. So in this receiver design, we have to use the one diode of AN4148, and the next is MPN, 2 MPN, which is 2N1711 and BC549, and the one battery, and the capacitor, resistor, and the one ion con diode inductor. So let we start to build out the receiver one step by step. Okay, here we done the build out of the receiver, and first we see this one is a diode type of the 1N4148, and this diode is made to prevent of the current flow break. Next is C1 and L1. The capacitor and the inductor this is form a tanker circuit, and to control the frequency of oscillation. And this Q1 and Q2 is a BC549 NPN, has a amplifier. So then this Q3 2N1711 is a demolator, also can be an amplifier. Next is C5 and R6. This is a filter to filter out the noise of the receiver. And this is a battery. And the resistor, capacitor. And important thing is this one R1. R1 will be set to 120K, and the 120K resistor will affect overall performance of the receiver. And the value of 120K is enough for use of the receiver to work well. The D1 will connect with the transmitter, and also from here we connect to the transmitter and let the whole antenna can be worked. So far, this is a whole design of the receiver. Next part, I will let my teammate to continue. Thank you.
Good day, doctor. My name is Ching Hui, and now I will present about the resource analysis in time domain. Before we start our simulation, let's talk about the setup of the oscilloscope. This is the digital oscilloscope in this Modulation simulation software. This oscilloscope has 4 input, and all of the 4 input we will put inside with different signal. The first input, the A terminal, we put as the input signal of our circuit, which is 10K. And the second input, which is the B terminal, we put it as the carrier signal, which is 1000 kHz, and it shown in voltage is 1 megahertz. And the third input, C terminal, is the output of the transmitter circuit, which is the output here, the transmitter circuit, and at the same time, this is the input of our receiver circuit. And the last last input is the output of our receiver circuit in the D terminal, which is here. The output of our receiver circuit. After the setup of the oscilloscope, next we will talk about how do we obtain the tanker circuit for the transmitter and the receiver, the capacitance and the inductance value. To obtain the capacitor and inductance of the tanker circuit, we will use this formula, and this formula we will assume that the inductance is 200 microhenry, and our carrier frequency is 1000 kHz. And rearrange the formula, we can obtain the value for capacitance is approximate 120 picofarad. So let's start our simulation now. So this is the interface of the digital oscilloscope, and here is the output window of the digital oscilloscope, and here we can adjust the 4 channel for the amplitude of the signal. And to simulate our simulation, we will adjust the amplitude are all the same, but since this one blue color is the carrier signal, it have a higher amplitude, so we will smaller the amplitude to easy for us to analysis. Okay, let's start with the first channel, which is the channel A. Okay, the channel A is our input signal with 10 kHz, and in the channel B, which is our carrier signal, since it have a higher frequency, so in this oscilloscope will show like a bunch of blue color things inside. We smaller the time range, we can see that is a sine wave signal. Okay, so the third input, which is the channel C, is our AM signal, the modulating signal. Here, this is the AM signal, and for the last input is the demodulated signal. This is the demodulated signal. Okay, so after that we will compare the shape of our demodulated signal and the input signal in channel A and channel D. So the yellow color is our input signal, and the green color is our demodulated signal. So we can see that the amplitude of both of the demodulated signal, which is the green color one, is have a higher amplitude compared to the yellow color, the input signal. So let's compare the difference between the input signal and the demodulated signal. We can observe that the demodulated signal have a higher amplitude compared to the original signal. This is because in our receiver circuit, there is a few stages of amplification, so it causes our demodulated signal have a higher amplitude compared to the original signal. Okay, that's all for me. Thank you.
A very good day to doctor. My name is Wong Chun Xiang, and matrix number AE180103. And today I will present the simulation part of the frequency domain analysis for transistor and also the receiver circuit. And first I want to mention to doctor is I will not simulate the result, because the result that want to simulate the Fourier analysis for 2 is 1 hour, and for 1 is 30 minutes, so it's very long time to simulate it. And I will show it, but I will not simulate it because it will take a long time. So the first step, we plot the probe voltage. We plot that here is the output of the transistor, and next we draw the Fourier analysis here, and after that we add trace. Add trace is the L1. We add the L1 and it hit OK. After that we simulate, we will get the Fourier analysis for the transistor, and we maximize it and we see it. The input signal that we input to modulate is 10 kHz and the carrier frequency is 1000 kHz and equal to 1 MHz. And we can see that here we have a frequency spectrum at 1 MHz, and this is show that the input signal we pass through the transistor and we had already modulated. And next, for the receiver is same. We plot the probe here and we draw the Fourier analysis and we add trace. This is the R13. We create the R13 and OK. And we simulate it. It will take 30 minutes. After that, we maximize it. And this is the output for this receiver circuit. And we can see it's 10K. It's same with the input frequency of the transistor, and this shows that the receiver had received the 10K and output it is same with the input signal of the transistor. And next, we see the spectrum at 1 MHz. This is the carrier frequency. The center of this is the carrier frequency, and this one is the lower sideband, and this is the upper sideband. And the lower sideband is 990 kHz and the upper sideband is 1.01 MHz. And we can compare it with our manual calculation. The LSB is equal to carrier frequency minus the input frequency. It's 1000 K minus 10K is equal to 990 kHz, and same with the lower sideband at the graph. And upper sideband is FC plus FM and equal to 1.01 MHz, and same with the 1.01 MHz shown in the graph. And after we have a lower sideband and upper sideband, we can calculate the bandwidth. The USB minus the LSB equal to bandwidth, and we minus it and we get the 20 kHz. And we find the bandwidth, we can divide 2, and we get the input signal frequency is same with the transistor, the input signal for the transistor. So that's all for me. Thank you.
Thus is the conclusion and recommendation. In the simulation part, the input signal and demodulated signal is in the same shape, but only the amplitude of the demodulated signal is greater than the input signal. It is because the demodulated signal is undergoing a field of amplification process. So next, in previous analysis, both output frequency spectrum of the transmitter circuit and the receiver circuit is 1 MHz, and it is same with the carrier frequency we select before, which is 1000 kHz. So, based on this result, we can conclude that our project is successful. About the recommendation, the limitation introduced require long time to get the simulated result in Fourier analysis. So that before simulate the Fourier analysis, please make sure that the circuit you are set up is correctly. That's all for our video presentation. Thank you for watching.